Hello everyone. Today we'll be discussing our latest technical paper, TBM Excavation in Himalayan Geology, over 1,200 meters per month at Bheri, Babai. Our presenters today are Brad Grothin, PE, Robbins Technical Director, and Missy Eisman, PE, Robbins Project Engineer. My name is Desiree Willis, and I'm Robbins Public Relations Manager. And I'll be moderating today's presentation, which will be formatted as a question and answer session. And with that, let's get started. So Brad, can you tell us a little bit about the Bheri Babai project and what you think are the most interesting aspects of it?
The Bheri Babai project is a hydroelectric project for 48 megawatts of power generation between the Bheri River and the Babai River, which we're not creative in coming up with names, hence Bheri Babai project. It also provides year-round irrigation, and so this is located in Nepal. They have some heavy seasonal rainfall, but then they have a long dry season, and so having that year-round water source along with power generation are really some of the more interesting aspects of it. It's made it a national pride project, so a lot of effort was put forth to make this project happen by a lot of the regional municipalities. And it was also the first project that involved a TBM, or mechanized tunneling, in Nepal. So it had a number of interesting aspects associated with it.
Great. And Missy, I know you visited Nepal early on to discuss the machine design. What were some of the factors in why they chose to use a Robbins TBM?
Yeah, I mean, this was a high-profile case for the Nepalese government, so they really needed a strong machine for the job. And, you know, Robbins has had a proven track record with rock machines, so we really felt like this was a good machine for the project. You know, the customer really wanted to have a lined tunnel to protect against fault zones. So, you know, to keep with this strict timeline that was really important to the project, we felt that a Robbins double shield was the best machine for the job. Because my double shields, it has a double thrust system, so you can bore at the same time as the segment lining is being built. So this way the tunnel can be constantly advancing.
And Missy, what were the ground conditions like, and how was the TBM designed for those conditions?
Well, for this project, the geological study projected around 823 meters of rock cover and at least one major fault zone, which is a big concern, that would projected around 40 cubic meters per second of water. And also a lot of the majority of this tunnel was located between two tectonic thrusts, resulting in ground conditions that can be weak and often fragile. So, you know, we needed to account for this in the design and make sure we had strong support system for these dangerous conditions. So one of the major things we did was we needed to worry about the squeezing ground that could exist. So we stepped the shield and incrementally brought down the diameter of the shield towards the tail. So the annular gap around the tail shield had more room in case of squeezing ground. It could contract and reduce the chance of getting stuck. Also, probe drilling is really important. So this machine was equipped with a large number of probe ports in multiple zones. This could give 360 degrees of coverage, and by probing and grouting ahead of the machine, it creates a sort of stabilized plug for the ground, and then the machine can bore through that and creating a more stable ground environment. Also, one of the things that in the end didn't get used, but we thought as a preventative measure, we thought we'd include shield ports radially around the shield in the gripper area to in case they wanted to add bentonite or other additives, and this could act as a lubrication to coat the surface of the shield and keep the machine moving in squeezing ground. Another aspect that we installed into the machine was ports around the crown for a possible four-poling system. This also wasn't used, but we implemented the ports in case it was needed later. So four-poling, in essence, we have ports in the crown at 22 degrees where they could be drilled, and then a rod can be inserted and grouted into place. And this, in essence, creates an overlapping pattern to stabilize the ground above the machine, making for a more stable tunneling environment. overall the ground conditions were better than projected. So, even though some of these systems weren't used, it's easier to plan ahead from the beginning and less expensive to put these measures in place ahead of time than dealing with the consequences of later not having them and the machine being stuck, and all the downtime isn't worth the cost of just having insurance ahead of programming these, just to have these systems in place.
Thanks, Missy. And Brad, I know a key challenge of the project was in how remote it was. Can you describe what it took to get to the job site and how the machine was transported and launched?
Sure. So for a lot of hydroelectric powers, they're obviously located in mountains or difficult regions. This one was no exception. It's located in Nepal's largest wildlife preserve. So from a transport perspective, obviously this isn't an exceptionally large machine, but we still needed to split the machine into multiple pieces, split shields, split cutter head, in order to be able to transport it to site. It's a wildlife preserve, so the roads, while fairly good for Nepal, were still fairly basic roads. It was a couple-hour drive if you just take a passenger car, a little bit bumpy, but to get some of these larger loads in took significant amount of time just because of the road conditions. There's multiple gates. The wildlife preserve is guarded by the Nepalese army, so there are several stop points or gates that you need to be able to go through, and then bridges that needed to be reinforced to take the high loads associated with the TBM. So not, compared to some projects, not exceptionally difficult, but there were certainly difficulties, and very far away from industry. So, and also power generation. So all the power needed to be generated using diesel generators for the TBM, and an on-site segment plant was set up, again, helping minimize the issues associated with its remote location.
Okay. And Missy, what were some of the challenges that the crews faced during tunneling?
Well, there were a couple issues that came up. Although pretty successful boring tunnel, there was 2 separate occasions where the machine encountered large amounts of water, around 2,000 liters per minute. And the plan was they inspected the ground, and luckily they deemed that it was stable enough to continually bore through with a slow pace. So in the end, they just had to increase the dewatering pumps, and they intensified the backfill grouting, and were able to slowly make it through that. So it saved a lot of time in having to stop and grout. Luckily the ground was stable enough they could make it through. There were 2 occurrences where the machine did become stuck. At one point, most of the tunnel up to this point was, the grain of the rock was perpendicular to the machine, which is the ideal circumstances, but at one point it shifted and became more parallel to the machine, and also the ground on the left-hand side was softer than the right, so it started to veer to the left. And as this happened, the machine got stuck, and so they tried to increase the thrust, and that wasn't doing it. So in the end, they had to make a small bypass on the right-hand side, and this loosened it up. And luckily that only took about 5 days, so it wasn't a huge disaster. But there was one other incident where a quick stoppage happened, where there was a large ingress of water and a overbreak over the crown of the machine, and these rocks ended up jamming the cutter head. To get it moving, they had to stop the water because it was so much that they injected about 1,200 kilograms of polyurethane grout, and this was able to mostly stop the water. And then they just applied some torque and were able to break loose and push forward and continue boring. So overall, not too many stoppages, and it was a pretty smooth tunnel.
Great. And Missy, I have also heard that the TBM achieved some really great advance rates. How do you think that they were able to achieve such good rates?
Yeah, we had great rates. It was an average of around 700 meters per month, with one high month being about 1,200 meters. And they ended up completing the project almost a year ahead of schedule, which was really great. And it was found that the geotechnical baseline report was often similar to what they expected, what they found, and oftentimes even better. So that minimized unexpected difficulties and, you know, kept the machine moving. A good example of this was they had planned ahead to have two types of segments, one with a higher reinforcement for difficult areas, and they thought around 73% of the segments would be the standard segments and 26 the stronger ones. And in the end, they only needed 8% of those stronger ones, and they used 92% of the regular segments. So that was a big factor in helping this machine go so quickly. One of the other things that really helped was the team was very consistent in, you know, they pre-planned everything, and they were very strict and consistent in their maintenance and their cutter changes, and really keeping to a strict schedule of all those. You know, oftentimes people need to keep a schedule, so they'll skip maintenance steps, and then you end up having a major machine failure or something because people weren't keeping strict with that. So I think the crew really played a big factor in maintaining all the daily stuff, and they also were daily checking the face and the tail for ground mapping, so they knew what was coming ahead, and they really took advantage of planning every day of what was ahead of them. Another really important factor was, you know, this was a long tunnel, 12 kilometers, and towards the end, it takes a long time to get the trains in. So they ended up having more trains and resources by methodically planning out the schedule of supplies. You know, you have to have segments to keep this consistent boring. You want to always have the supplies you need. So they were meticulous about keeping all the supplies they need on hand and getting the train schedule timed out right. So all those factors really helped to just keep all the gears moving and everything on track. So it was pretty successful.
Great. And Brad, now that the project is complete and you can look back on all of tunneling, would you still recommend a double shield TBM?
You know, it's pretty hard to argue with success. So in 2020, hindsight is always a benefit. So I think the double shield machine was absolutely the right choice for this job. As Missy mentioned, the geology ended up being on the favorable side, which definitely, you know, allowed the machine to make maximum advance rates. So the contractor was good, so they were able to take advantages of the additional features that machine had, and then obviously coming out with basically a finished tunnel at the end where you don't have to do, you know, lining after the fact, all really led to a successful project. And so trying to mess with success would probably be a mistake. And I think things went to plan, which is really what a good project does, proper planning and execution. And I think this is a good example of doing that.
And given the overall success of the TBM, Brad, what do you think that means for future TBM tunnels in Himalayan rock?
It's for Nepal in general and just that region. I think it's was a great project. It really showed people what was there. I mean, any new technology that you're trying to bring into an area, there's always some apprehension, especially with the amount of investment that's required in a large tunneling project. And so it really showed what was possible in that region, and all the benefits that can be realized from this technology being applied. They were the lower Himalayas, and like Missy said, the geology was well understood and ended up being a little bit friendlier. But we have obviously additional technology that can be applied to the machine as we evaluate all these different projects that are there that have been proven out, that can be very successfully, I think, applied to projects in the country. So you need, for a successful project, obviously buy-in from a lot of different parties besides just the technology to make for a successful project. And this project had that. I think it really helps for future projects seeing this level of success.
Great. And I have one last question for both of you. So if you could each summarize today's presentation into one key takeaway for our viewers, what would it be?
I think planning is so important. I feel like, knowing the surroundings, knowing the ground conditions, knowing, what to prepare for was really successful on this project, and planning ahead by applying, equipment to the machine that could save you in the end, and important for situations, especially in the mountains. It's difficult to know, and also just really sticking to, your schedule, and maintaining the machine is so important. So I think those really helped in making a successful project.
In a lot of complex projects, there are a lot of different hurdles that need to be overcome, and how you overcome those is really key to success. This project had a great owner that was very dedicated to making this project happen, and a strong contractor, and I think a well-proven technology, and then of course the geology was, supported the overall project. But when there are difficulties, having that owner, strong contractor, having that relationship along with good equipment is really key to making it a success. And an example of that, like I said, they had generators on site. So it can be as simple as making sure Nepal had a fuel shortage for a little while there, and the owner worked with the contractor to make sure that they had what they needed to complete that project. And that's just an example of, something that we take for granted that needs to be overcome for that project to move forward.
Great. Well, thank you, Brad and Missy. This was a great informative session. And for our viewers, be sure to check out some of our other technical paper recordings from 2020 conferences, which will be released throughout the year on our website, therobbinscompany.com. And now it's time for our 10-minute Q&A session. Brad and Missy are here live for your questions, so please use the Q&A button at the bottom of your screen to submit a question to us. So our first question we already have. Missy, what were the major risks considered during the TBM design stage?
Well, first of all, I think the biggest risk that they were worried about is, you're going through the mountains, and fault zones are always a big risk. They knew of one large one that I talked about earlier, and before boring, you just have to, the best thing you can do is get as much geological mapping as you can, and, use rule of thumb values for overburden, and just try to design accordingly. And, it's always easier, like I mentioned, to put preventative measures in place first, and then to deal with getting stuck. So and that was the biggest concern, is just the fault zones in the water. And, I worked on a previous project where it was a competitor's machine. They were in the mountains and they got stuck, and the pressure was so high that the shield got crushed, and there was a cylinder, like one of the thrust cylinders was halfway down the backup. So these things aren't to be trifled with. They're really dangerous, and it's important to make things strong enough and put enough measures in place ahead of time to be able to encounter bad situations like this.
Great. And Brad, what was the maintenance routine like during tunneling, and how were spare parts made available to the machine?
Sure. Missy did speak a little bit. The contractor did a great job of maintaining the machine. They were very rigorous in their approach to that. It was a remote job site, and there's not a lot of heavy industry in that area. So parts supply, as the question kind of leads us to, is a critical aspect of keeping the machine and the project running. So it was a job site job. They had some facilities there, but they also they concentrated a lot on their supply chain. So they had critical spare parts at site, but then they also made prior arrangements to have supply fairly locally, but then also from China, Japan, and of course the US, to make sure the machine was able to be maintained and moving forward.
Great. And Missy, could you talk a little bit about the cutters used and the ideal cutter type for this kind of geology?
It's most important on stuff like this. We use backloading cutters, and with a typical cutter spacing, and you know, with a geology like this, it's always safest for the crew to be able to load from behind and do maintenance that way. So that we implied, I believe they were 17-inch backloading Robbins disc cutters, and they were pretty successful. There was pretty low wear cutter rates, so there wasn't a ton of changes that had to be made.
I can add to that a little bit. It was a fairly weak sandstone, and so it wasn't a real challenging cutter job. You know, as we evaluate different types of cutters, it was, in many ways, it was a very good cutter job. There was some sandstone was a little bit of abrasive, but overall it was a pretty straightforward job as far as disc cutters were concerned.
Great. And Brad, I have one here about Elon Musk. According to promotional statements by Elon Musk's The Boring Company, the speed of tunneling can be increased by a factor of 10, while the cost of tunnels can be cut by a factor of 10. In light of the impressive performance in Nepal, do you think that statement is feasible? And what do you think the traditional tunneling industry is doing to address the challenge?
What I would say is Elon Musk does a great job of creating a lot of excitement. Sometimes that requires pretty bold statements to be made. So I will just take it as a positive that he has definitely created more excitement around tunneling, which I think is great and exciting to see, and really pulls interest into the topic. Whether that's achievable or not, individual machine advance rates, instantaneous advance rates, that might be a little bit difficult. But as we look at projects as a whole, which let's say I'll give them credit for, hey, if we look at a project as a whole, the planning stage, all the different levels that one of these projects need to go through, the tunneling aspect of it is pretty short. So there is definitely potential there. And if nothing else, get more people at least talking about the subject and excited in tunneling, which I think is great.
Okay, and Missy, have there been any other Robbins TBMs designed with these same features for difficult ground? And do you think those features have been proven in challenging geology?
Yeah, the most widely used one is drilling. Most of our machines have probe drills on them. It's very important to know what you're drilling, what you're boring into, and also they're helpful with being able to grout the space around you. So that's widely used on most machines. And we've definitely used the step shield technique on a lot of machines. It's just an easy way to give a little more space in the back, like I talked about. And similar to that, we use a shimming technique for overboring. When needed, you can just shim the gauge cutters, and that gives you a little more space in the annular gap for squeezing ground. And it's also an easy way to, when you don't need that anymore, you can remove them and save money on extra grout. So we use that a lot. Some of the things that we didn't use on this machine, but we've been using for, difficult ground, or where we've been implementing 2-speed gearboxes on quite a few of our machines lately. And that offers you a low speed, high torque option for when you're in difficult situations. And something that we were talking about putting on the machine, but didn't end up doing, is a more comprehensive sealing system that we've used before, of putting emergency seals around the articulation joint and the gripper areas, and also sealing up the muck chute in the front. So we have implement these on machines where we've helped when a lot of water's coming in to better seal off the machine. So there are quite a few things that we've used in the past that have proved to be useful.
Great. And Brad, do you think this project is part of a larger trend for seeing more tunnels being bored in mountainous and high cover conditions in the near future?
Certainly in Nepal, there's been overall, tunneling in mountains has been around for a long time, and there is, in certain sections of the world, increased interest in that, in part for hydropower, like this project was, or combined power. And in Nepal, it's been great to see, for this project especially, how a successful project that is on time and decreases the cost of tunneling really opens up development possibilities in the country that needs it. So there are a number of schemes that have been brought forward as of late because of this project that have now become economically viable. So worldwide, that's certainly the case, and definitely in Nepal, where they can see, firsthand see the impact of a successful project like this.
Great. And Missy, would you say there were any factors that slowed down production or caused delays?
There weren't, just other than the few stoppages that I mentioned earlier in the conversation, there weren't a lot of slowdowns. Like I said, they kept supplies moving forward, and they were really good about just moving forward with tunneling. So there weren't a lot of issues that slowed production down.
One thing that maybe I can add to that, when a contractor does a good job, they can make a potentially difficult project, seem a little bit, not to use a pun, but boring, straightforward. So there was definitely some situations that would allow for stoppages and, a little bit more of a disaster story. But again, like we talked about, the spare parts or logistics, or there was fuel shortages at the time. So a lot of steps were taken to make the project run smoothly on the logistics side, just across the board. So the contractor did a good job, along with the owner, of mitigating a lot of those risks to make it run smooth, make sure it runs smooth.
Great. And Brad, is there a minimum practical size for a double shield TBM? And what is the range of double shield TBMs that Robbins has produced thus far?
Is there a minimum size? We do have, we call them small boring units, but in many ways they move down into the pipe jacking range. So 2 meters, there's changes in functionality. Really, it starts to become a matter of the segments. So when we talk about a double shield itself, we're erecting segments or pipe jacking, but depending on the lining type, we go down quite small with those, 2.5 meters. So it really, I hate to say it depends on the application, but it really, depending on the lining and the distance, is gonna dictate how small we can go with this type of technology.
Okay, and Missy, how important would you say a skillful local crew is on such a large scale project?
Oh, I think it's huge. If you have most of the workforce, or if they're bringing people in, or if they're hiring local, you have to have a skilled crew. And I've been on projects before where they've had less than stellar operators and crew, and like Brad mentioned, if you plan right and you have people doing their job and working well and planning ahead, then it's smooth and there's less hiccups. So skilled labor is always so important in projects like this.
Okay, and I think we have time for one more question. Brad, could you say that this project being small diameter was a positive point and made it easier for the excavation?
Well, this was, it wasn't an exceptionally small diameter, but it was on the verge. It was smaller, let's say. Real small machines have a lot of challenges associated with them. The sweet spot, you hit about 5 meters to 8 meters, where in that range, it gives you enough room to work inside the machine, but the face is very manageable. You get really small, and there's a lot of challenges just on the logistics side of keeping the machine fed and working in that small of an environment. So Smaller is not always better as far as the machine is concerned when it comes to advance rate, just because of equipment size. So I wouldn't attribute, the short answer is no, I would not attribute the diameter or the smaller diameter to the success of the project. Honestly, having the geology was a little bit better than was originally predicted, which, you know, that can't be overstated. You know, they did certainly hit some challenging ground, but there was more challenging ground with less water than they originally predicted, which definitely benefited the job.
Okay, great. And that's all the time we have for our Q&A today. If we didn't get to your question, we'll send you a follow-up email with a response. After you exit today, you'll receive a survey link. Please take a few minutes to take that survey. We use your responses to improve our future events. Thanks and have a great day.